Hopefully, as we've been talking about solving higher order differential equations, you've been getting this feeling of there's a lot more higher order differential equations out there than you're giving me the tools to solve. And it's true. So far, we've only talked about what do we do if there's constant coefficients. What if those coefficients aren't constants? Or we talked about the method of undetermined coefficients, but we needed g of x to be some specific type of function in order to be able to use it. So what happens if g of x just isn't as well behaved as we would like? What can we do? How can we solve these things? There's a method called variation of parameters, and that's what we're going to use to solve more broadly higher order differential equations. Before we jump into higher order differential equations, let's talk about linear first order differential equations again really quick. So remember when we were solving these, namely the linear first order differential equations that looked like the derivative of y plus some function of x times y equals some other function of x. We used an integrating factor to help us solve these. And we got a solution that looked like y equals c1 e to the negative integral of p of x dx plus e to the negative integral of px dx times the integral of e to the integral of px dx times f of x dx. It's really nasty when you don't do all of those integrals and you just write it all out that way. But it falls into this form where we have y equals y sub c plus y sub p, which is a form that we've been seeing as we've been working on solving lots of differential equations through this. So let's take a look at what it would look like to solve this linear first order differential equation using variation of parameters. Well, we would look at this and we would say, you know what? If I'm looking at dy dx plus p of x y equals 0, that homogeneous differential equation, well, I know that e to the negative integral of px dx is going to be a solution of that. So I know that there's a general solution, c1 times that y1 solution. Variation of parameters isn't satisfied with just like constant multiples of this. Instead, what we want to find is some function of x times this y sub 1 of x. We want that to be the particular solution we're trying to find. So what we're going to do is we're going to substitute u1, y1 in for y into our dy dx plus p of xy equals f of x equation and see what happens. So we'll be taking the derivative of u sub 1 y sub 1 plus p of x times u sub 1 y sub 1 equals f of x. Taking that derivative, we get u sub 1 times the derivative of y plus y sub 1 times the derivative of u, our product rule in action there, plus p of x u1 y1 equals f of x. Now, if I factor out a u sub 1 where I have a u sub 1 to factor out, what I end up with is u sub 1 times the derivative of y plus p of x y sub 1 plus y sub 1 times the derivative of u equals f of x. Since y sub 1 is a solution of my differential equation, dy dx plus p of x y, then equals 0, then I can substitute 0 in for dy1 of x plus p of x y1. And in doing so, I'm left with just y sub 1 times du1 dx equals f of x. Using separation of variables, I can solve this differential equation now. So I'm left with just d u sub 1 on the left-hand side because y sub 1 is a function of x, as is f of x. So I'll be dividing by y sub 1 of x and multiplying by dx, and then I'll be integrating both sides, which will give me u sub 1 equals the integral of f of x divided by y sub 1 of x dx. Now, I wanted y sub p to be equal to u sub 1 times y sub 1. So I'm going to substitute what I found for u in. So I'll get y sub p equals y sub 1 times the integral of f of x divided by y sub 1 of x dx. Now remember, y sub 1 equals e to the negative integral of p of x dx. So substituting that in for y sub 1, I find myself with e to the negative integral of p of x dx times the integral of e to the integral of p of x dx times f of x dx. That's the same y of p that I had. So this method works to be substituting in u1, y1 as a solution and then figuring out what u1 has to be in order for that to be the case. So let's take a look at it with a second order differential equation. So with a generic second order differential equation, we have the second derivative of y plus p of x times the first derivative of y plus q of x times y equals f of x. I want y sub p to look like u1 of x times y1 of x plus u2 of x times y2 of x in this case. So taking the derivative of yp, I find that I've got u1 y1 prime plus u1 prime y1 plus u2 y2 prime plus u2 prime y2. And taking the second derivative, again, lots of product rules applied there. And I get this lovely derivative. So now that I have derivatives of what I want to be a solution to this differential equation, I'm going to substitute them in as the particular solution that I'm looking at and figure out what u1 and u2 need to be in order for this to happen. So I'm going to substitute in y sub p prime, and y sub p double prime in for y double prime, y prime, and y into my differential equation. In doing so, I get this incredibly long thing, and I can factor a u1 and a u2 out of parts of it. And when I do, I get u sub 1 times the quantity y1 double prime plus p y1 prime plus q y1. Well, we assumed that y1 is a solution to the homogeneous version of the differential equation, so that means that that is all equal to 0. And it eliminates a decent chunk of terms for me there. And then I also have u2 times y2 double prime plus py2 prime plus qy2. Well, we assumed y2 was also a solution to that homogeneous differential equation, so that also equals 0. So what I'm left with is two copies of u1 prime, y1 prime, plus u1 double prime, y1, plus two copies of u2 prime, y2 prime, plus u2 double prime, y2, and plus p times the quantity u1 prime y1 plus u2 prime y2 is equal to f of x. Now, rearranging stuff a little bit, I can recognize this as the product rule has been applied a couple of times, namely to u1 prime y1 and to u2 prime y2. So what I really have here in this sum is the derivative of u1 prime y1 plus the derivative of u2 prime y2 plus p times the quantity u1 prime y1 plus u2 prime y2 plus y1 prime u1 prime plus y2 prime u2 prime equals f of x. So this is really the derivative of the sum u1 prime y1 plus u2 prime y2 plus p times that same sum plus y1 prime u1 prime plus y2 prime u2 prime equals f of x. And then since I'm taking the derivative and p times some, like the same sum, if I make an assumption that that sum actually equals 0, it simplifies this a huge amount. It actually makes it be y1 prime u1 prime plus y2 prime u2 prime equals f of x. So that's an equation, and actually that assumption is also an equation. So I have a system of two equations now, namely u1 prime and u2 prime. So we're going to use Cramer's rule, which tells us that solving that system of equations, u1 prime must equal w sub 1 divided by w, which equals negative y2 times f of x divided by w. And u2 prime must equal w sub 2 divided by w, and that's also equal to y sub 1 f of x times w. Now w is our Wronskian with y1 and y2 in it, in the matrix, along with their derivatives. Y sub 1 takes the first column of that matrix and replaces it with 0 and f of x instead. While w sub 2 takes the second column and does the same thing. And of course the w's, the vertical lines, are telling us to take the derivative of that matrix, like we did for our Wronskian before. So that tells us what u1 prime and u2 prime are. So if I want u1 and u2, I need to take the integral of each, and that'll tell me what u1 and u2 are. When you do that, when you take that derivative, there's no need to put constants into it. You can leave those out. And also it's worth mentioning that you might end up with u1 and u2 values, or u1 prime and u2 prime values, that you can't integrate very well. And that's okay. You might end up in that situation, and if you do, it's okay. Finally, should mention that all of this generalizes to whatever order differential equation that I want to deal with. We've been dealing with a second order one. We looked at how it worked, but it works for any order. It's a really long, involved process. So there's very few times when I feel like the right answer is to memorize something, but this is one of the times when I feel like the right answer is to memorize something. You should remember how to generate w sub k. So remember, you take the kth column and replace it with the solutions to the equations you're trying to solve. So in this case, it was 0 and f of x in my second order case. So if I want w sub 1, it's the first. If it's second, if I want the seventh, I would replace the seventh column with this. And the Wronskian's always the same. And that fraction, w sub k divided by w, is going to tell me what u sub k prime is every single time. And so I can find all of my u sub k primes, take the integrals of them, and I find myself knowing what all the uk values are. And so I know what my general solution is to my differential equation. So that's what's going on with variation of parameters. And again, like I said, one of the few times, remember this, and then you don't have to remember how to get to this along the way. It's very, very worth remembering.